Hello, welcome to episode 171 of Quarkus Insights. It matches up quite neatly because we're going to be talking about Hibernate Search 7.1 and vector search. So the only thing that would have been tidier is if we'd had Hibernate Search 171. But I guess that will be a few more releases anyway.
Right.
So we've got with us, we've got Marco and Yoann. So I guess let's start with introductions. So do you want to go first, Marco?
Okay. I'm Marco. I'm part of Hibernate team, and I've been working on Hibernate Search and other Hibernate projects for a while. And that's it, I guess, from me.
Yep, cool. Thanks. How about you?
Yeah. Same Yoann Hibernate team. I've been working on Hibernate Search for several years. Like 7-8 years.
Wow.
And now I'm trying to let Marco do more of that work, and so he'll be presenting you a lot of his recent work on vector search, and I'll be there if there's a need to provide more context, I guess.
Excellent. We can send all the hard questions to you.
Oh, that's the idea.
Cool. So I guess with that, do you want to jump in, Marco?
Yep. Yeah, sure.
Yep. Shall we share your screen?
No, we can start sharing. So for today, we wanted to talk about Hibernate Search, and with vector search, this is a recent addition to functionality. It is available in 7.1, so it is already in Quarkus if you want to try it out there. And we thought we'll start with a quick demo. So what differences are there between full text search that was provided by Hibernate Search for years now, and what vector search can bring you in your application? So we'll start with what everybody already knows about search. And let's try to find some books. So we have this application that lists books, and we have a search filter for a search query, and then some simple drop down with the filtering capability here. So let's search, for example, for a wizard. If you try to do that, okay, let's refresh. We find some Harry Potter books, and you'll notice here, once we entered the search query, there are some highlights. There are some synonyms configured. For example, in this case, sorcerer and wizard are treated the same. Another thing about full text search, we see that we were searching for wizard, but it also found words like wizarding or wizards. So all of that is what everybody used to when they are doing full text search. What vector search can bring us is something a bit different. So it's more about finding similarities, and to demonstrate that, we have this additional option for searching to find similar books. So let's try to find a book with the Ink Heart, with the title Ink Heart, and try to find similar books to it. So if you try to do that, a list of books will be listed down here. And it's important to notice that in the database or in any other storage, there is no notion, there is no connection between this particular book and whatever books were found in this list below. So all of that is just finding similarities between the reference book that we were looking for and other books in the storage that we have. So you notice if you look at the cover of this book, you'll notice there are 2 persons of that book, and then in the similar books that were found, there also are people on the covers there. Even on this one, it seems like there's none, but if you look closer, there's actually a person here as well. And on this one, there's 2 people here as well. So the idea is that instead of trying to find exact matches or matches on words, you can try find something similar to what you're looking for. Or we can try to look up another book. So we were searching for wizards. Let's try to find Potter Order. Yeah.
There's a typo.
Yeah,
There's a typo.
there's a typo. Order. Yeah, so if you're trying to find similar books here, you'll notice it'll find other books from Harry Potter series, as well as it'll find another book from this universe, these fantastic beasts. And the way we build this application, this demo application, we find similarities between covers and between the descriptions of the books. So that's why it's possible to find books similar to what you're looking for, and they actually look similar. So I hope with this short demo we got our audience interested in what vector search can bring in. And I'll let Yoann talk a bit about Hibernate Search in general, so what it is. And after that, we'll go back to vector search.
Yeah. Did you unmute me? Yeah. So
probably want to share something, maybe.
I'm sharing my screen right now. Basically, what Hibernate Search is about is transferring data from your database to another dedicated solution for search. So you have an entity graph in your database, and Hibernate Search will integrate within Hibernate ORM, track the changes you make to your entities in order to update a copy of that in the index. And it's not just a copy of each row in your database. It's really at a higher level. Like, you have entities which refer to other entities, and this kind of forms a tree of what you want to index, and you will be able to map that to a document that is stored in either Elasticsearch, OpenSearch, or Lucene. Why those solutions? Well, it's because they provide very advanced search features. Traditionally, it's been full text search, so a search on words, but they've added lots of other features over the years. So Scala search on numbers, of course. There's a geospatial search, and more recently, there's vector search, which, if you have it all in a single solution, can help a lot develop integrated solutions. How it differentiates from other, perhaps more obvious batch solutions, is that it keeps your data updated as you change it in your database. You make a change in Hibernate ORM, and right away Hibernate Search will update it in Elasticsearch, for example. And so you can have a search that is closely matches the current state of your database. You don't have to reindex every night, for example. Now, where it comes handy is, so yeah, there's a whole thing that goes on every time you change your entity. It's completely implicit, right? There are listeners installed in Hibernate ORM, and Search will just do its job to make sure it's updated. For the application in particular, I think Marko has something to show how it works exactly in his demo, and perhaps we should switch to that.
Okay, so let's talk a bit about the differences of vector search and full text search. So with the full text search, we have some text data. We send the text data to our search backend. So what Yoann just mentioned, it can be either Lucene or maybe Elasticsearch, OpenSearch clusters. You send the text data. There is this concept of analysis in the world of the full text search. In short, through analysis, you'll produce a list of tokens, and these text tokens will be stored in the index, and then they'll be searched upon. While with the vector search, the difference is that, first of all, you can work with other types of data, so it's not necessarily text, but you can also work with multimedia data like images, maybe some audio files or video files. It all depends on whatever model you can find, or maybe build yourself and train it. The thing is that you just need to pass your data through this AI model, which can produce an embedding vector, and then this vector will be stored in the index. Usually this model, it lives outside of your search backend, and you can think of it as sort of a black box.
But
now,
it allows you to judge a book by its cover, which
yeah,
I love.
that's the thing. And another difference is that with the text data, so in the end, you'd be actually searching for full matches on the tokens. So your search query will also go through this analysis process. A new set of tokens will be generated for your text query that you're trying to search for, and the exact matches will be looked for in this index. But with a vector search, you will still feed your data through the model to generate the vectors, but then you'll be trying to find similarities, so you won't be finding exact matches. Maybe there'll be an exact match for particular document in there, but usually you'd be looking for vectors that are close to each other. And that's basically the difference here, because with the vector search, you would need to specify how many similar documents you want to find. And you need to be careful there, because you might find documents that aren't really similar, just because it takes the amount of documents you want to find. So you need to be careful. But we'll talk a bit about that later through demo, where we have some ways to address this problem. Now, let's try to look at how you can work with the application, so with Hibernate Search, and how you can actually make it search something. So you need to start with populating your index. And if we are talking about simple case, so just for the full text search, you would have your text data, and you'll send it through your, maybe through your endpoint, or maybe in some other way. But the point is that you would be working with the text data. Let's assume that you're working with the endpoint, so you'll send that data through an endpoint. Then there'll be Hibernate ORM and Hibernate Search. You'll be working just with Hibernate ORM here, so you won't be working directly with Hibernate Search. And as Yoann mentioned earlier, with events in ORM, Hibernate Search will subscribe to those and listen to whatever changes you're trying to make to your data, and then populate the index in the end, while Hibernate ORM itself will store your data to the database. Then once you try to perform some searches, in that case, you'd make some request. That request would go through your endpoint. So let's say you're trying to find books with detective in description or title or anywhere in the text bar. So you'll send that request to your endpoint, and then build a Hibernate Search query through its DSL, and Hibernate Search will call the search backend and return your results to you. Now, if we are talking about the vector search, it gets a bit more complex. So if we try to look at the way you would need to populate that index, how you would save your data, you would have your cover image, you would have your text information, and once you send it to your endpoint, you would need to somehow get the vectors from the model. So there can be two ways you can do that. You can either call the model directly yourself, get the vector, and then write that vector into your entity, or you can create this bridge. It's one of the components that Hibernate Search provides. And that bridge will call the model for you once it would need to create a document to send it to the index.
So the difference here is that in one case you store your vector in the database, and you can potentially reuse it. That's the top solution. And in the other case, you would regenerate the vector every time you reindex your entity.
Yeah, thank you. That's correct.
What's the advantage of doing it the second way? Because it seems like it would be really expensive.
So yeah, it all depends on what the model you have and how fast it is. So for example, with this approach, you would generate the vector once, save it, and just reuse it all the time. But then it means that you actually need to save it in the database. So that would take your disk space on the database side, right? And if you have a robust model that's quick enough, then maybe you can save some storage on the database side and just regenerate the vectors when you need them.
And beyond the storage space, you also save yourself some effort, since if you do it in Hibernate Search, you know that it will always be done. If you do it in your endpoint, you have two different endpoints that change your entity, and you forget to update one, well, you're done. It won't be updated automatically. In Hibernate Search, it's declarative. We'll see how it's done exactly, but you basically tell Hibernate Search this property should be transformed with this bridge, and it will be done all the time.
Right. So that's how you'd index your data, and then when you'll be searching for it, so you still need to work with those vectors. So let's assume that example of finding similar books. So let's say we want to find a book similar to the book with ID 32, then we need to send that ID to our endpoint. Our endpoint eventually would need to call the database to get the vector for a cover image. So we can use that vector to create a query for Hibernate Search to find similar books. And then because we have these two approaches, one is to store a vector in the database, another one is to regenerate every time you need it. So you would actually also need to call this embedded model to get your vector for a text part, and then use two vectors that you've created and you've got from the database to create a query, send it to the search backend, and get your books back. So if we try to compare how it's different from the regular search. So you see, in this case with the vectors, you need to have those vectors somehow. Either you store them in the database and you get them back once you want to search, or you regenerate them from the model. While in the case of simple full text search without any vectors, you'll just work directly with your search backend. You don't need to call the database. You don't need to make any calls to AI models. You'll just send the data through to your search backend, and that'll be it.
So part of the difference comes from the fact we're doing a different kind of search too. Like in the case of vector search here, we're taking one book and trying to find similar books. In the case of your full text search here, we're taking a text request, and trying to find books that match that request, which we could perhaps do with a vector search as well. It's just that it's not the most obvious use case here when you're using this solution.
Now, let's take a look how it actually works in your application in the code. So where it all starts is with the mapping. So let me make this bigger. let's start with a simple entity. So in this case, we have the author entity, which is actually used as embedded entity, and all you need to tell in general to Hibernate Search to make things work is just map your entity with some annotations. In this case, we're using the full text field, so we want to apply some analysis to this text. We also seen that if you go back to the application here, to the demo, there are some highlights. So that part, if you want to enable that, is also done here in the mapping. You'll just tell Hibernate Search that you'll be using some highlights for your search queries, and this part will enable that for you.
Maybe I should
If
show the mapping on my side.
Yeah. That would be nice.
Can you switch the screens, Holly, please?
Thank you.
Thank you. Yeah. So basically, we are starting from a classic Hibernate or M entity, a JPA entity. So it's a class. It's annotated with entity. It has an ID. So various JPA attributes, a title, and so on. So that's the book entity. And if we want to have this duplicated into an Elasticsearch index, we add the @index annotation. By default, it will use the entity ID as document ID in Elasticsearch. And yeah, like Marco explained, we need to also annotate which of the attributes we want to store in the index, because you don't want to store everything. You may not want to store all the columns, basically, from your entity, and you may also not want to recurse in all the associations. So in this case, when you want to also embed another entity into the document form of your book, of your entity, you need to specify it explicitly. Why? And why would you do that in the first place? It's because you don't have joins in Elasticsearch. So you need to denormalize your data. If you want, when you search for a book, you want to filter by author name, for example, you need to have the data about the author within the document that represents the book. This needs to be denormalized. Fortunately, you only need to specify it's denormalized, and Hibernate Search will handle all the complicated aspects itself. Like if you have a change in the name of an author, obviously it needs to reindex a book, and it needs to retrieve the corresponding books and reindex them. And that's handled implicitly by Hibernate Search. But the point is, what you will do here is declare that your book is indexed. You will declare what you want to index. You will declare potentially other entities you want to embed into the book document in your index. And before we had full text search, you would stick to this. And with vector search, you just add a new type of field. The thing being, here, when we talk about fields, we're talking about index fields. So it's not just about specifying the type like string or integer. It's about specifying the search operations you want to do. Because for each operation you will need to do on your data, you will need to store the data in a certain way to optimize this operation. Like the full text search in Lucene and Elasticsearch is super fast because the index is optimized a certain way to match what you need. So those are mapping options that you will set on your on each field you declare for your book. And I think we'll get back to this one with Marco. I don't know. Yeah, it's probably later or no?
No, I think we can take it right now. Yeah, so as you were saying, the vector field is something new. It's related to this vector search, and it's probably worth to mention a slight difference in the configuration. So usually to change this analysis process that we were talking about once we were trying to compare these two approaches, so this analysis process, right? With the full text search, you need to configure it to your needs, and that's done with this analyzer or search analyzer. But with the vector fields, you need to specify some attributes that are based on your AI model. So you need to take a look at the documentation of it and figure out what's the best options to pick. In particular, what the vector similarity function to choose, because with the dimension part, it's something fixed. So the AI model would produce a vector of constant size, and you need to check the documentation of it to figure out what size of that vector is prior to annotating a field. Then, if you take a look, we have this other vector field. So that's the difference that we are talking about. You can either store your vector, so pre-generate it somehow, and store your vector directly in your entity, so it will be stored in the database, or you can use, like in this example, some regular fields, maybe a string or maybe something else. But in this case, it's just a string summary. And then you can apply this value bridge that would do the work for you. So if you try to go to this bridge implementation, then we'll see that there is this embedded model that is called by Hibernate Search itself whenever it needs to create a document before sending it to your search backend. So this way, you wouldn't forget to populate the vector, and it'll actually get indexed correctly for you. Yep. Sorry. So next part, let's take a look how it actually works on the search side, because we talked about the mapping. Maybe not, but let's actually take a look at how the entity is saved. So if we go to saving process, as we mentioned before, you don't actually need to do anything related to Hibernate Search when you work with your ORM entities. That's all happening in the background. So there are these listeners to ORM events, and you are just working with your ORM entities as usual. So you either find it in the existing ones, or maybe you create a new one, persist it, update your fields, and so on, and that will get reflected in your index automatically. Now, if we go to the searching part, so let's start with the simple full text search. So that will be just finding books by a string query. So you would start doing that from a search session. With Quarkus, you can actually inject it like a bean. So this is part of Hibernate Search extension in Quarkus. You'll just inject it and then start building a query through the DSL that Hibernate Search provides. In this case, we are using projections, so you don't need to hit the database to get the results back. You'll be just working with your search backend. If you look at the projection itself, so that's also something relatively new in Hibernate Search in terms of annotating your parameters of projection constructor with annotations, projection annotations. So you see we have some highlighted projections, some regular field projections here. And yeah, so let's go back. Okay. let's go back here. And then you build your predicate in the where clause. So in this case, we have some filter on the genres, then we build the search query on multiple fields. And also we have configured a highlighter to show the highlighted results, so where the text query matched in the document. Now, if we go to the similar book search, so that's where we are talking about the similarities, the vector search part. In this case, as we were talking about earlier and showing on the diagrams, we want to get the book back from the database because that's where we stored the vector for the cover image. So we need to get that vector for our search query. That's why we are looking up it from the database. But then, as you see, the process of building the query is quite similar. So we're still using the search session, still trying to use the projection, the same projection actually, for the book. And then we are building the predicate. But in this case, we are using this vector search predicate. It's specific to vectors, the canon predicate. And it starts by specifying the number of documents, number of similar documents you want to find. So that's where you have to be careful, and you need to play around to figure out what the best value is for your particular use case. In our scenario, we have two vectors, so we've added them as two should clauses here. Why we've done that? Because what we wanted to achieve is that we wanted to find books that are similar either in cover or in the text description, or maybe both. We didn't want to combine them through AND condition. That's why we've used this these two should clauses where we added the canon predicate. You also notice here this additional configuration of the canon predicate, the required minimum similarity. So this is something quite useful if you are trying to find similar items, but there might be cases that there's not enough similar elements to find, and results closer to the end of the list might seem like garbage. So to remove those items from the list, you can use this required minimum similarity filter, and what it'll do for you, it'll just remove the documents for which the similarity between the vector you are searching for, so this cover vector and the vectors in the documents are not similar enough. So that will just cut it out. If we, for example, if we go back to the application, I think that this particular book, so it wouldn't have any similar covers if we try to find it. Yeah, so you see it says, sorry, no similar books found. But if we try to modify this query, so if you try to say, okay, let's try to find any book, and also let's remove this one for the text. So hopefully now, if we try to search, it starts finding more books. But I guess covers are not that similar, and maybe descriptions are, but yeah, I know. The idea here is that when you try to build this query, you need to test it against your data. You need to find the numbers that actually would work fine for you. So when we were creating this application, we just played around with it and tried different values to see what works best on the data set that we had. Another interesting part of this canon query is this filter part. So that's also something you need to consider when you're doing the vector search. In our case, because we are looking for similar books based on the book that's already in our data, it means that the book itself will be the most similar one, right? It'll be an exact match. So we want to remove that book from the list. And it's important to do it through the filter because if we do it outside of canon predicate, then it would mean that this canon predicate would actually find this book, the one that we are using as a reference, but then it'll get excluded by the where clause if, for example, we would add this filter outside. So something like filter. Let's try that. So yeah. And that would mean that we would find less books than we specified in this total. So that's also important to keep in mind. Let me check what else is there. Right, another part, what might be also interesting. So we were talking now just about finding similarities. So it sounded like you can do either full text search or vector search, but actually you can combine them both together, and that's what mostly is recommended actually. In this particular demo application that we had, using just vector search worked nicely because of the idea that we have to find similar books. But you can build your predicate using full text search and similarity search for the vectors altogether. And actually, we already have this filter on genres, which is not exactly a full text search, but it's part of that. What we can try to do here is we can try to add another clause. For example, we can try to add a clause to find some books with a particular keyword. So let's say match field summary, and then let's say matching detective. So let's try that. Now, if let me refresh it. So now if you try to find similar books, you'll notice here that we've got this investigator or detective. So these words are getting highlighted because we've added this additional predicate to our similarity book search, and now it's actually a combination. So we get similar books in covers, but we also are including full text search. For example, in this case, we are finding investigator, even though we were looking for detective. And that's because we have some synonyms configured for our full text search.
And that's actually a way to take advantage of vector search for your general search, like the what book do you like above. You could consider running both a full text search and a vector search on your data, and having Elasticsearch merge the results and give you the results that best match on both sides of the query. And it's useful because, like you saw in full text search, a lot of it is explicit. If you want to handle synonyms, for example, you will have to be explicit that detective is a synonym for investigator, for example. And with vector search, it's not quite how it works. You have a black box which has been trained to consider that things like detective and investigator are basically the same thing. And it doesn't work on words, it works on something that happens to work and to produce similar vectors. I won't tell you how because I don't know, and most people don't know. That's kind of the point. So the idea is that by combining full text search, which will find you reliably rather similar documents, and vector search, which will find you perhaps fewer relevant matches, but will find some interesting ones that would have escaped full text search. By doing both, you will be able to improve the relevance of your search overall. And it works great with Elasticsearch because both features are supported out of the box, and you have other features that you can combine. Like if you want to combine geospatial search with that, you have let's say an application that searches for shops, and you want to look for, I don't know, food pictures, and you want to find the shops around you. Well, basically sky is the limit. You have all the search features available in Elasticsearch that you can combine any way you want. And that's the power of going this way instead of perhaps sticking to what's available in, I don't know, perhaps your database that doesn't have all these features, or going with a dedicated vector store, which happens to handle vectors very well, but has little features apart from that.
And we've just had a comment come in, which I did not know. So Yoann has pointed out, did you know that Gerald Salton introduced the vector space model in 1975? So this seems like such a new technology, but the foundations are not that new.
Right. Well, I don't know about the specifics of vector space in computer science, but I mean, vectors, the concept of vector space is like more than 100 years old. It's math from the last century. So the applications are, I think, what's important here. And yeah, I didn't know it was from 1975. What's interesting is that even vector search, applied vector search, has existed for more than like 2 years. But with ChatGPT and stuff like this going live and making the headlines the past few years, a lot of these technologies are emerging to a wider audience, and a lot of databases, data stores are working a lot more on these features because they are trendy, which is ultimately great for users because you're getting yet another tool to add to what you can do in your application.
Yeah, we've just Yoann and I have been just both Googling as well. So so there's a useful reference to Wikipedia. And if anyone wants to go really hardcore, that is the academic paper. And it's a vector space model for automatic indexing. And we've got a question that's not about 1975 academic papers, which I think will be a relief to everybody. So Narciso asks, hello, Quarkus folks. I joined a little late, but I'm curious to know if this approach supports natural search. For example, recommend a good horror book.
So I may be able to show something about this.
Cool.
What you're after here is natural language processing. This is typically not what vector search is about, but it's more about what large language models are about. You will have a different kind of model that doesn't produce vectors, but that might use other models that produce vectors. But the idea is that you will ask a question in natural language. This model, like the previous one, will be a black box. You don't know how it works, but you don't really care. Ultimately, it will produce an answer that seems relevant at first sight. And hopefully will stay relevant when you look a bit more into it. Typically, the problem with these models is that they are large. They require large infrastructure to run, so you don't typically run them yourselves. Though, from what I understand, you can for some of them, and it's being increasingly likely. But even if you could run them yourself, what you want is to customize them with your own data. And customizing such a model with your own data means training. It means having data scientists work on that. Personally, I'm a software developer. I'm not a data scientist. I don't even write Python. So I don't know how to do that. And I think most software developers don't either and don't really want to learn, because that's a job in itself. That's a lot of work and knowledge necessary to train a large language model. So an alternative is retrieval augmented generation, which is a big name for something really simple when you think about it. You, instead of sending a question alone to the large language model, which doesn't know about your particular data, you will send a question and some context that you have extracted from your own data. While why just some context? Well, because uploading your whole database might be a bit long, and you might not want to extract everything and give it to OpenAI or whoever. I don't know who. So you will essentially go through a first phase where you use something that has extracted your data, indexed it, and when you ask the question to the large language model, you will perform a search based on the question here. You will put it through the search pipeline, get an identifier of your matches, get back the data from these matches, and add this to your question. Give it to the LLM, which is basically this. The insides of what happens here is not really what you're interested here, but the fact that you need something to search your data and to give back that data to the application so that it can transfer it to the LLM is the heart of what Hibernate Search will help you with here. So there are multiple ways of doing that. You could do simple full text search. You could do vector search as well. You could potentially use a vector so Holly knows probably a lot more than I do about this, but you could use a vector that has been generated like by OpenAI and send the vector directly for the RAG. I think that's one option. Or you could send just the raw data over to your LLM. Anyway, just to summarize, vector search is not natural language search, but it can help with natural language search in this solution.
Cool, thank you. I was thinking about what you were saying earlier about the vector embedding uses, and then you kind of drew the blank, because it's as many of us do. And I really like Vicky Boykus from Normcore. She talks about a shift to search which is based on vibes, and I don't think that's the technical term, but I think it's actually being used quite a lot now to describe that thing that we can't really describe.
Yeah, and it's also interesting because it's actually not really a replacement, but it can complement a full text search, where you have more strict requirements, like not even just full text search. Like you can have filters on your metadata on the genre. Well, I can't pronounce that in English, but on
Which is hilarious.
geolocation, for example, and you can have full text search, which is sort of halfway between those strict criteria and what an AI will do. And then you have AI to augment and to find just a bit more results that could be relevant to your users and boost those, because it seems there's really something relevant in there, but you cannot really find it by any other way than using some black box that seems quite smart, but you don't know how it works.
Yeah, I think you're right, and I think that's probably going to be a lot of the kind of the skill and the art going forward in this area, isn't it? Of like knowing when to combine the kind of the new vibes LLM magic vector stuff with the old stuff, and it's in that combination that we get the most optimum results. Whereas if you go just, let's replace everything with an LLM, it will look good for about 5 minutes, and then you start to discover the gaps where actually it either gives the wrong result or it gives the right result, but with much, much greater cost. But then if you don't have any of it, then as well, you're in that case where sometimes your users can't find what they need, or it takes them so many queries, and doing something that had a bit more of that vector embedding or a bit more of that kind of black boxiness finds the right thing.
Right. Yeah.
We've got a follow-on from Inercido saying that totally makes sense and provided a great deal of detail. Thank you so much. And yes, we built a gift finder powered by OpenAI, sending some inputs, and the model was trained with our product data. And he adds that he's also a software engineer, and they had a team with a software engineer and a data engineer, and that's what you do.
Right. And I'm guessing this data engineer was quite useful to the process.
Yeah. So how are we doing? Have we got more demo?
I think that was it from us.
Cool.
Yeah.
Yep, that was really, really useful, really interesting. So any final thoughts? Final questions, anybody?
Perhaps some updates on what's next in Hibernate Search. So right now, I don't know what's been merged already. Maybe Marko can talk more about that. I know that one of the new things we've been working on in Hibernate Search 7.2 is more aggregations, and hopefully the ability to nest aggregations. So basically, this is useful when you do applications with faceting, where you see when you search for articles on e-commerce websites, you will have a summary of how many results you have for each category, and that's one of the things where you want to get search results on one side, but you also want to have aggregations of how many items matched in each area of your shop, and you might want, in some cases, when it's not just a shop, you might want more advanced features, like you might want a sum that on an average to be computed, but at the same time you're retrieving the results. Like there's a single request and you get all the necessary information. That's what aggregations are about in Hibernate Search. Some of them are already available, and there's work to improve that by our friends from Infinispan, actually.
Cool. And we've got another question too. Coming back, I think, to this to this discussion we were having earlier of like how do you combine the various technologies that all seem to do sort of similar things but potentially give you quite different results? And so the question is, Jude is asking how it compares to LangChain4j.
Right. So I'm not an expert in LangChain4j myself, but I know that a lot of LangChain4j is about building your pipeline yourself. So you will explain, or you will describe basically how to extract data from somewhere and how to push it to your vector store. And then when you do a search, you will use, I think there's a neutral language nowadays in LangChain4j for search and filtering, but you will use LangChain4j for search as well. In Hibernate Search, then first one difference is that we're not trying to target all vector stores. We're strictly about Elasticsearch, OpenSearch, and Lucene, basically the Lucene world. And we're trying to integrate tightly into Hibernate ORM so that you don't have to build the pipeline. You describe on your entities what will be indexed, what will be transformed to a vector. And Hibernate Search will give you the ability to either run a mass indexer to process your whole database and send everything to Elasticsearch, for example, which will take time, of course, but you don't have to write that code. Just going from your mapping, Hibernate Search will do the thing for you. And once you've initialized Elasticsearch, and that's the more important difference, I think, Hibernate Search will be able to detect any change you do through Hibernate ORM to reindex the relevant documents and only the relevant documents. So it will keep your vector store, if you will, which is Elasticsearch, up to date at all time. And that's probably for different use cases, because you cannot really do that if you have huge gigabyte long documents that you want to update to index. But on the other hand, that's a much simpler solution that you can apply quickly to existing applications. So there's a trade-off, I guess. If you want to go to the full solution where you can do anything you want, use any vector store you want, use any pipeline you want, you will probably go with LangChain4j. If you have an application already, you are using Hibernate ORM to access your data already, and you want to add powerful search on top of that, then Hibernate Search might be the solution to explore first. I hope that helps.
Yeah, makes sense. Thank you. And can you remind me, because I know for the search on the Quarkus website of the Quarkus docs, we switched to Hibernate Search a while ago. Are we using the vector search there, or are we just using vanilla search?
Well, I guess Marko can take that one.
We are not using vectors yet. But if you find some use case for it, maybe we will. But for now, it's just a full text search, and it is pretty powerful as it is without vectors. So, but yeah, if you find a good model, or if you can build that model and train it, then it definitely can enrich your search experience with vector search. So.
Yeah, makes sense. Oh, and another question, again from Jude, is there a plan to also support non-Lucene databases like Postgres and pgvector?
Well, if somebody wants to use pgvector, then that's already in Hibernate ORM, because ORM works with the databases. So if somebody wants to explore that, it's been there for a while now. But with Hibernate Search, it's more about this Lucene world. So we see in Elasticsearch OpenSearch.
Right.
Makes
The
sense.
idea is really to move your data from the database to somewhere else, which, by the way, has other advantages, because you could, in an application with few writes and lots of search, you could scale your search horizontally a lot by using Elasticsearch without changing your database much, and without changing the resources you use for your database. So that's more the spirit of Hibernate Search, to denormalize and externalize search rather than going through your database, which Hibernate ORM already does, like Marko said.
Got it. Cool. So we've been going for an hour, and we've had lots of good questions, and I think we're done now, unless there's any final questions, any final comments. Nope. Okay, that's all. We're good.